Hello everyone, this is our mission science briefing for MAVEN. Still on schedule for a launch at 1:28 p.m. on Monday. We'd like to start with a brief status of what is going on with MAVEN and the Atlas V at the launch pad, and things are relatively quiet. This is a crew rest day for the launch team. Everything is in readiness at the pad. The only activity going on is battery charging of the MAVEN spacecraft and monitoring of the state of health. And our weather forecast for Monday has remained the same, a 40% chance of no-go, primarily due to cloud constraints, and then 60% no-go on Tuesday and on Wednesday because the wind will increase some on Tuesday and Wednesday. So Monday remains our most favorable day, 40% no-go or 60% go. And at this time, all is in readiness to pick up the countdown at 6:28 a.m. on Monday morning. We'll start now with our presentations. First, Michael Meyer, the lead Mars scientist from NASA headquarters in Washington. Bruce Jakosky, the MAVEN principal investigator from the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Janet Luman, the MAVEN deputy principal investigator from the University of California at Berkeley. Nick Schneider, the MAVEN IUVS instrument lead from the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Paul Mahaffey, the MAVEN NGIMS instrument lead from NASA's Goddard Space Flight Center in Greenbelt, Maryland. And David Mitchell, the MAVEN SWIA instrument lead from the University of California at Berkeley. And we'll begin first with Michael Meyer. Michael.
Well, thank you, George. For millennia, Mars has been a source of myth and fable. And it's only a little over 50 years ago that we first sent a planetary probe into space to move from just myth and fable to actually observation and measurements. If I could have the first graphic, please. Our sister planet Mars has been the focus of planetary exploration primarily because it's a key to understanding the origin and evolution of our planets. And so over a little over a decade, we've had spacecraft, orbiters, and landers that have worked synergistically to help unveil what is happening on Mars and what may have happened in its past. And as we see MAVEN, here we are getting ready to launch, and is going to answer a key question about Mars evolution. And with that lead into, as we can see, other spacecraft that are either international, as in provided by ESA or by NASA, going into a future of very robust Mars exploration and trying to not only tell us about the evolution of climate and geology, but also of life. So with the next graphic, I'd like to say, while we've been doing all this, what have we learned? Well, one of the things that has been unveiled is that looking at Mars and looking in the near subsurface, we see that Mars has actually quite an inventory of ice, water ice, in its polar areas. And we look more at the geology and mineralogy of the planet, we can see that water once flowed on the surface of Mars. At least that's what it looks like. But with rovers going to the surface and landers going to the surface, we see mineral evidence of water having been at the surface of Mars. We see hematite and we see gypsum discovered by the Mars exploration rovers. And just recently, with the rover Curiosity, we found a rock called a conglomerate. This is the type of rock that we only find on Earth in dried riverbeds. So we now have evidence with other measurements showing that there is water flowing on the surface of Mars. We know that it was the environment at one point in time on Mars was able to support microbial life. But you look at the Mars today, it's cold, it's dry. We want to know what happened. And with that, I'll turn it over to George to lead the rest of the conference.
Thank you, Michael. And now to Bruce Jakosky. He is the MAVEN principal investigator from the Laboratory of Atmospheric and Space Physics at the University of Colorado at Boulder. Bruce?
Thank you, George. Michael talked about the geological evidence that there was water on ancient Mars and the mineralogical evidence. Something clearly happened. Water was abundant on early Mars. The environment was something that was capable of supporting liquid water. Yet today we see a cold, dry planet that is not able to support water. What we want to do is to understand what are the reasons for that change in the climate. In order to in looking at the drivers of the change in climate, we're going to be able to understand the history of the geology of the planet and the history of the potential for life, the history of the habitability of the planet, because both of these depend pretty much on the history of water, the history of the environment, the climate on the planet. With Mars having had liquid water early on, we think that there must have been a thicker atmosphere that would have produced greenhouse warming so that the planet was warmer early on, and something happened. What we want to do is understand, where did the water go? Where did the carbon dioxide from an early thick atmosphere go? There are two places it can go. It can go down into the crust where it can get locked up, but we don't see the evidence for widespread, abundant carbon-bearing minerals in the abundance necessary to be a reservoir for that thick early atmosphere. The other place these could have gone is up to the top of the atmosphere, where they could be stripped away and lost to space. The removal process would involve forcing by the sun from solar wind, from solar extreme ultraviolet photons from light waves, from solar storms that might strip away gas from the top of the atmosphere. MAVEN is all about trying to understand these loss processes, understand what could have happened at the top of the atmosphere and how gas could have been removed from it. Now, we can't go back and study what happened over 4 billion years, but we can go and look at how these processes are operating today and how they might have changed, how the processes might have changed over time, and what the integrated effect would have been. Can we go to the first graphic, please? We've selected 8 instruments, 9 sensors, so there are 9 boxes here, to make the measurements. We want to understand all the different connections in the chain from the energetic drivers to the response of the structure and composition of the upper atmosphere to the escape to space. In the upper left on the chart here, you see 4 instruments that are focused on measuring the energetic input from the sun, the properties of the solar wind as it hits the atmosphere, the solar extreme ultraviolet light waves, and the solar storms. Each one of these is capable of driving processes that can lead to escape. In the lower left, you see the instruments that are going to be measuring the properties of the ionosphere. The ions are created when solar light strips an electron off of an atom or a molecule, and the ions have a specific set of processes that can lead to escape, and we want to understand what those were. In the lower right, you see the instruments that measure the basic composition and structure of the upper atmosphere today and tell us about the things that can lead to escape. With these 9 sensors, we're able to make all of the measurements that we need in order to understand what role has been played by escape to space. If you go back to the graphic, please, I also wanted to focus on the spacecraft here. The instruments are arrayed around the spacecraft, each one able to make the measurements that it needs at the same time so that we can get measurements throughout the orbit. The instruments are at the end of the solar panels, at the end of booms, or an articulated platform at the bottom so that they can be oriented relative to the planet. The spacecraft is in an elliptical orbit around the planet designed to allow us to make these measurements. It goes from the lowest point in the orbit, about 150 kilometers altitude, up to 6,000 kilometers. From the high point, we can make observations of the whole planet, and we pass through the upper atmosphere on every orbit. In addition, 5 times during the mission, we're going to lower that lowest point to 125 kilometers, and that lets us sample the entire upper atmosphere, all the way down to the well-mixed part where it connects to the lower atmosphere, and all the way up to the top where it connects to the solar wind. Even though we're passing through the atmosphere, it's so tenuous that it just doesn't create much drag on the spacecraft. We'll feel it, but it's not going to affect our orbit very much. We're going to hear from the rest of the panelists from the deputy PI, who's going to talk about some of the processes, and we have 3 of the instrument leads to talk about how the measurements will let us go to this question of how much gas has escaped over time. So I'll turn it back to you, George.
All right, thank you, Bruce. We'll talk now with Janet Lumen, the MAVEN Deputy Principal Investigator from the University of California at Berkeley. Janet?
Thank you, George. If we can start with my first video. The sun is a major player in this mission, as Bruce has said. The Earth is thought to have had its atmosphere protected somewhat by its magnetic bubble of a relatively strong internal field, but Mars only has very localized remnant magnetic fields that form small umbrellas of protection, so that the atmosphere is more or less exposed most everywhere to the onslaught, the direct onslaught of what's coming from the sun. May I have the next slide, please? This is an illustration, a very complicated one, of what we think the various processes at work are in removing the atmosphere of Mars at the current time, and presumably throughout the history of Mars since it settled down from its initial formation phases. What we find is that it's a hugely complex system with a lot of inputs and outputs. The sun is producing, in addition to the radiation, the photons. It's producing these gusts of solar wind called coronal mass ejections. It's producing energetic particles. And Mars is responding in various ways, literally bristling with loss processes. MAVEN is instrumented specifically to be able to measure what's coming in and what's going out, and how the output responds to the input. This will allow us to estimate over long time periods, the order of billions of years, which is the age of the solar system, how long Mars has been exposed to this kind of loss process, and therefore how much atmosphere could have been removed in this way. May I have the next video, please? We are fortunate that the sun has been predictive in some sense. We are going to be arriving at Mars at the time of the blue arrow next September. And the sun, even though the sunspot number has been fairly modest by previous standards in the space age, the sun has been quite productive of these conditions that you see on the right in the Soho movie of coronal mass ejections, which is a very recent movie, giving you an idea of the fact that the sun is definitely not a quiet start this time. We expect it to be active when MAVEN arrives, and we will be able to sense the arrival of these gusts of solar wind and all the associated particles and fields, and hopefully understand the response of Mars. The early sun was supposedly more active than the current sun, and so we expect that these active periods that we're seeing in the solar maximum will better represent the history of Mars, the early history of Mars, for our purposes of going back in time. And I will pass it back to you, George.
All right, thank you, Janet. And now to begin our discussion of the instruments, Nick Schneider, the MAVEN IUVS instrument lead from the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Nick?
Thank you, George. MAVEN has 2 instruments on board that measure the composition and structure of the Mars atmosphere. And those instruments are the imaging ultraviolet spectrograph that I lead and the neutral gas ion mass spectrometer that you'll hear about next. And these instruments operate in very different ways, but they provide complementary information. So I'll talk about how we figure out what's in the atmosphere and how it's distributed around the planet, how and why we make those measurements, and I'll be emphasizing the imaging ultraviolet spectrograph. So our instrument takes advantage of the fact that the entire atmosphere is glowing at ultraviolet wavelengths. And the graphic will explain how we can take advantage of that glow in order to understand what the atmosphere is made of. If you could bring up that graphic. If you run electricity through a tube of gas, it glows. This is the principle behind fluorescent lights and neon signs. And the example that you see in the graphic is a tube of hydrogen gas. And to the eye, it glows pink. But if you spread that light out by looking through a prism or running it through an instrument like ours, what you see is not the full rainbow of colors, but just the specific colors at specific wavelengths of light. And that is the spectroscopic signature. It's the fingerprint of hydrogen gas. And every gas has its own unique fingerprint. So even from a distance, when we take a spectrum of it, we know what gases are there. So wherever we look with our instrument, we can figure out how much carbon dioxide, how much oxygen, how much hydrogen there is, even off at a distance. Let me show you how this plays out in flight. And this is a model of the MAVEN spacecraft. It's about 30 times smaller than the actual spacecraft. And normally the spacecraft keeps the solar cells and instruments oriented towards the sun. So any instrument that we want to study the planet is mounted down here on this movable platform. So whichever way the spacecraft has to move in its orbit and whichever way the spacecraft needs to be oriented, we can ensure the proper direction for our observations. Now, I think of NGIMS as the nose of the spacecraft. It's right here, and as we skim down through the upper layers of the atmosphere, NGIMS is basically sniffing atom by atom, molecule by molecule to figure out what the composition of the atmosphere is right at the location of the spacecraft. Now, at the same time, our instrument is looking off to the side in the distance at the glowing atmosphere. And not only can we look in a single direction, but we have a moving mirror that allows us to scan up and down and see the composition of the atmosphere as a function of altitude. And at times when we're far from the spacecraft, we can actually map out those ingredients over the whole globe of the planet. If I can hand that over to you. Thanks. Careful.
Got it.
The reason we're studying the composition and structure of the atmosphere is it reveals to us how much energy the atmosphere is receiving from the sun. And at times when there's excess energy input in the form of those harsh ultraviolet photons or particles from the solar wind, it has a number of effects on the atmosphere. And the first thing that it does is it puffs up the atmosphere. That extra energy heats it up, and we can measure that with our instruments. And the second thing that happens is that that excess energy causes chemical reactions, and it can break apart molecules, and it can strip the electrons off of atoms and create ions. We can measure all of that. The excess energy in all these forms also causes extra atmospheric escape. And so as we're making these measurements, studying the properties of the atmosphere, we're very sensitive to how the input conditions are leading to atmospheric escape. Now, we'll be paying very close attention at the times that Janet referred to of high solar activity, because those are the times most representative of the early sun. And so when we're measuring the escape rates during periods of high solar activity, that's our best guess about how much atmospheric escape was occurring billions of years ago. And we add up that level of atmospheric escape over time, we'll have a good sense of just how much atmosphere Mars lost through escape to space. Back to you, George.
All right, thank you, Nick. Now to Paul Mahaffey, the MAVEN NGIMS instrument lead from NASA's Goddard Space Flight Center in Greenbelt, Maryland. Paul?
Thanks, George. Delighted to support the mission with the provision of the mass spectrometer to study the upper atmosphere physics and chemistry to contribute to the study of atmospheric loss in the current time, and then ultimately to contribute to our understanding of ancient Mars, ancient climate, and the habitability conditions on ancient Mars. As Nick mentioned, we're kind of the nose of the mission. We have a mass spectrometer that as we go down in orbit to the lower altitudes, primarily below 500 kilometers, we measure both neutral gas. I'll illustrate how we do that in just a second. And then we also sample gases that are ions already in the atmosphere that solar radiation has produced. And so we sample those both over the entire mass range of about 2 to 150 Daltons to see what we get, but we focus in on particular species that we believe are there that we want to get a higher spatial resolution with. Bruce selected an instrument payload that was very complementary. As Nick mentioned, the UVS kind of gets the global view. It'll be measuring things like carbon dioxide and molecular nitrogen, atomic oxygen, and so on, and very much get a global view over the planet, whereas we pretty much get a very detailed view, but just along the spacecraft track. So we'll be making measurements on every orbit as we dip into the atmosphere, and during these periods of the mission where we do the deep dips, we'll get even more signal going down to the point where the atmosphere is well mixed. We're also very complementary to the fields and particle suite of instruments. For example, the static instrument measures a range of energies of ions up to very high energies, and we measure the composition of ions as well at lower altitudes, but at the lower energies. So the UVS, the static experiment, and the mass spectrometer all complement each other very nicely. We're interested particularly in how the spatial distribution of these atoms and molecules changes with altitude, and that really ties to these processes of atmospheric escape. Let me give you one example. We have, for example, with the Curiosity rover, measured a suite of atoms and molecules in the well-mixed atmosphere. And one atomic species that's particularly interesting is argon. The primordial isotopes of argon are argon-36 and argon-38. And of course, the 38 is a little bit heavier. The 36 is lighter, so it ends up going up higher in the atmosphere on average, and it escapes easier. So over billions and billions of years, you leave more of the heavy stuff in the atmosphere. And so we measure that both with surface landers, we've measured that with Curiosity, but we'll really get an idea of the distribution of these things in the upper atmosphere with our MAVEN NGIMS experiment. So I have to show a picture of the instrument developed by our talented engineering team at Goddard. What you see on the left is actually a protective cap for a break-off. When we get into orbit around Mars, we'll fire a pyrotechnic, that cap will come flying off and eventually land on Mars. But then the ionization source of the mass spectrometer will be exposed. And on the second graphic, I'll just remake the point that we're down on the surface with our rovers, with Opportunity now roving on one part of the planet, and Curiosity shown in the left graphic on the left. And the study of Mars really is a program. You need to look at things both in detail on the surface and understand what's happening with the upper atmosphere to really get at the history of the planet. And so, in fact, we have a mass spectrometer on Curiosity. It's in the SAM suite. And the advantage of being on the surface is we can not only look at gases that were trapped in an ancient environment that we release by heating, but we can measure the current atmosphere very, very carefully and with high precision. So for example, in that argon isotope measurement that I just described, we were able to get a very precise ratio of argon-36 to 38. It turns out to be about 4.2, very precise number. And that's really different than any place else we know of in the solar system. And these are primordial argon isotopes, and that's just really a signature of the lighter argon having escaped over billions of years easier than the heavier argon. And so we'll be looking at a range of isotopes and chemistries that go on in the upper atmosphere with our MAVEN mass spectrometer as well. So what I'll end up with is just a little bit of a snapshot with a video, which you can look at now, of how the mass spectrometer works. So this is basically a metal case, and what you see here is an electron beam, an illustration of electron beam that's ionizing the neutral gas in this case. It sees a molecule in the beam, it breaks it apart, it creates an ion from a neutral gas. That ion then gets focused into a quadrupole filter. It's a set of 4 rods, and as the ions spiral down the rods, they get separated out by mass. They hit a detector, you count the number of ions that come through at a particular mass, and you have what's called a mass spectrum. And that's how we measure the composition of the upper atmosphere. So that's how our instrument NGIMS works, and with that, we'll pass it back to George.
All right, thank you, Paul. And following on to complete our discussion of the instruments is David L. Mitchell, the MAVEN SWIA instrument lead from the University of California at Berkeley. David?
Thank you, George.
I'm going to talk about just a couple of the processes that Janet showed on her complicated graphic. In the simplest terms, an atmospheric species at Mars has to attain escape velocity to leave the planet. For neutrals, this can occur via exothermic chemical reactions in the atmosphere and also by impact by energetic ions. May I have the first graphic, please? For ions, on the other hand, these are charged particles, and so they can be accelerated by electric fields arising from the interaction of the solar wind with the Martian ionosphere and with its crustal magnetic fields. However, these same crustal magnetic fields can form closed loops and trap the plasma on these closed loops so that it cannot escape. Nearby magnetic field lines are open to the solar wind, and they allow ionospheric ions to go out into space and be lost. This is a two-way street. It also allows the solar wind plasma to precipitate down and heat the ionosphere below. On MAVEN, we'd like the formation of these regions of open field lines are analogous to auroral zones on Earth. And it's a dynamic process, and they open and close as the planet rotates and as the solar wind magnetic field changes strength and polarity. On MAVEN, the SWIA and the MAG instruments are designed to map out the crustal magnetic fields and determine whether or not they're open and closed. The magnetometer measures the field's strength and direction, and SWIA measures electrons flowing along that field line to determine whether or not the field is open or closed. And this sets the stage for the interpretation of all the plasma measurements on MAVEN. However, this is a region with strong crustal magnetic fields, and Mars does not have strong crustal magnetic fields over the entire surface. There are large regions, particularly in the northern hemisphere, where there are very negligible crustal magnetic fields. And in these regions, the solar wind is able to interact directly with the Martian ionosphere. One of the key regions for ion loss is the interface between the solar wind and the top of the ionosphere. In this region, the ion density is relatively high, and acceleration to escape velocity can lead to significant ionospheric loss. If you could please start the video. Here, we see a simulation of ion loss from the top of the ionosphere at Mars. You actually see two processes at work here. At high altitudes, there's direct pickup by the solar wind as it flows past the planet. Those are illustrated by the white arrows that are shimmying around. Of interest here is the plasma instabilities that arise at the solar wind ionosphere interface. And you can see those at the bottom, where large portions of the upper ionosphere are literally stripped away and carried downstream of the planet. So on MAVEN, we have a suite of instruments that are designed to study this interface in detail. The SWIA instrument measures the flow of the solar wind as it passes by the planet. SWIA, MAG, and LPW study the structure of the interface. And STATIC measures the composition and velocity of ions as they leave the planet. So our goal here is to try to understand the importance of these kinds of processes to the overall loss of atmosphere at Mars. And with that, I will pass it back to you, George.
All right, thank you, David. And we're ready now to take questions. Please give your name and affiliation when the microphone comes to you. Questions over here? All right, right here in the front.
Hi, I'm Miriam Kramer with Space.com. I'm wondering, the instruments I think are supposed to be turned on about 2 weeks into the flight, and I'm curious if there will be any measurements taken en route to Mars and what those measurements might be.
Let me start. We're going to turn the instruments on to check them out, make sure they survived the launch successfully. That's the primary focus of getting them on as soon as possible. Some of them will be taking measurements during the cruise phase. We'll be doing observations of the sun in order to compare with the Earth. And Nick, do you want to say something about possible observations of Comet Ison?
Sure, I'd be happy to. If we launch on time and if the top priority of the trajectory correction and all the other checkouts go okay, we'll have the opportunity to use our ultraviolet imaging spectrograph on Comet Ison. Many of the same gases that are present in the Mars atmosphere are also present in comets. And so what an ideal opportunity for us to try out our instrument and do some good science along the way. We're crossing our fingers, of course, about the successful launch and successful checkout. But we should, if we have the time, get some really great observations in the ultraviolet of Comet ISON.
Bill Harwood, CBS. I'm not sure who to ask this to, but when we're talking about these methods or ways that the atmosphere gets stripped out, I'm a little unclear about how those work on Earth. Is the magnetic field the predominant thing that prevents that same sort of escape, or is, I don't know how much gas gets replenished in Earth's atmosphere from the geology. That's one question, was just comparing the two a little better to explain it.
Would you like me to take it? This is a subject of debate in the science community, in fact, whether the presence of a magnetic field does shield the planetary atmosphere. The workings of the escape, there is escape in both cases. The workings of the escape processes are different. In the Earth's case, for example, the magnetosphere takes the brunt of the solar wind impact, but some of the energy is channeled into the polar regions mainly. And so there's a focus of the energy that helps produce things like the aurora. And also geomagnetic storms can be produced by the impact of some of these coronal mass ejection pressure pulses. So there's energizations going on, but they're different kinds of energizations. And so the way it works in the Earth is that the energy gets into the polar regions, stirs up, heats the ions, and then they flow out of the polar cap. And then they have to make their way out of the magnetosphere. So even though there's an energy input and a heating process, it's focused into the high latitude regions. It heats, and the ions that are heated have to run the gauntlet to find paths out of the magnetosphere. However, estimates are that the current day escape rate for an important element such as oxygen and oxygen ions at the Earth is presently comparable to what's been measured at Mars by the Mars Express spacecraft and the earlier Phobos spacecraft. So current day rates of oxygen loss, anyway, are comparable. What we want to determine is whether the rates scale with solar inputs in a different way at Mars, where we have the direct interaction with the upper atmosphere rather than the filtering by the magnetosphere.
One more quick one.
If I could follow up
sure,
on the answer on that, I'd like to point out that one of the processes that Bruce mentioned was suspected at Mars has definitely occurred on Earth, and that's the absorption of atmospheric ingredients into the planet, into the crust itself. And so that's where most of the carbon dioxide given off by volcanoes has ended up on Earth. And so that process has definitely changed our atmosphere here. The other thing I wanted to emphasize, that even though we do know that atmospheric escape is happening from the Earth, there's no way that our atmosphere will lose the habitability of our planet. We have both a magnetic field and strong gravity. So it's a very different story for Mars in the past.
Thanks. And I don't know if you can answer this or not, is Mars today, would you guess, but not as part of the reason for the mission, but is it nearing a steady state? Is there some lower limit to where you wouldn't expect to lose a lot more and it would just stay there, or could you lose it all if enough time goes by?
What has happened on Mars is that the most intense loss is thought to have occurred early in the history when the sun, the solar wind were more intense. The loss rates today are low enough that we're probably not going to see the loss of the entire atmosphere. The reason we're studying it today, even though the loss rates are so much lower, is that we can understand the specific processes that are going on and learn how to extrapolate them backwards in time.
Do you have any additional comments you want to make on that, Michael? Okay. All right. Let's go right here.
Frank Mooring with Aviation Week. I think this is for Bruce. Nick mentioned that you're using some data or comparing some isotope data from Curiosity. I wonder, is there any specific coordination planned among the various spacecraft at Mars with MAVEN?
We are looking at coordination between the different spacecraft. The reason we need to do that, the reason we want to do that, is that Mars is actually a very complicated system. We've gone beyond the ability to look at one part of the planet and understand everything there is to know about it. The atmosphere connects to the upper atmosphere and to the solar wind and lost to space. It connects to the surface, the polar caps, the deep interior. So we need to understand all parts of it, and that requires comparing observations from different spacecraft. With Curiosity, as Paul mentioned, we're comparing the isotopes we're going to measure at the top with the isotopes at the bottom. We don't need to do any specific coordination because both spacecraft are going to be working, doing their own thing, and we can compare the data after the fact. Where we think we can do the most valuable coordination is with the European Space Agency Mars Express mission, because they have several instruments that are measuring things very closely related to the things we're measuring, and we want to make sure that we're getting the right observations at the right time to be able to do that cross-coordination. We have a working group made up of members of our team and members of their team for the specific purpose of doing that coordination. We've also approached the Indian space mission to Mars, Mangalyaan, in order to discuss whether there should be coordination there, because they also have a couple of instruments that make relevant measurements to what we're doing and vice versa. There we've agreed that after we're both in orbit taking data, we'll figure out what coordination we need. I'm suspecting that it'll be after the fact comparison of data rather than coordinating the observations, but we've agreed to look at that after we both get there.
Okay, Ken?
Hi, Ken Kramer for Universe Today and Rocket STEM Magazine. I'd like someone, maybe several of you, to talk about why you chose this particular elliptical orbit. I think the tenuous atmosphere is extremely more tenuous at the higher 6,000 kilometer altitude. So why did you pick this orbit? Why are we not having an elliptical orbit that's closer into the planet? When are these science instruments making their measurements? Is it mostly when we're at the lower orbit, or is it continuous throughout?
Let me take a start at that, and these guys can chime in as well. We picked the orbit for two reasons. One is with an elliptical orbit that goes as low as 150 with occasional deep dips down to 125, we get to sample the entire upper atmosphere. So the in situ measurements pass through the important parts of the atmosphere on every orbit. At the highest altitudes, the IUVS instrument can do imaging of the emission from the atmosphere to tell us about global composition. So that elliptical orbit with that low altitude and high altitude lets us get the measurements we need. We picked that particular orbit as well because the gravitational torquing from the planet will cause it to precess. The plane of the orbit will rotate with respect to the line from the sun, and that will let us get different local times relative to the sun. And it also precesses in latitude, so the latitude of periapsis, the closest approach to the planet, sweeps between plus and minus 75 degrees. So that gives us relatively complete coverage in all three dimensions. Throughout the orbit, we've divided it up into segments, and each instrument makes its measurements, makes its most important measurements at the altitude range that is most important to it. So IUVS and static focus on the high altitude parts. At the other end, the NGIMS instrument and static and IUVS focus on the low altitude parts, and everybody takes measurements in the middle. Everybody's taking measurements most of the time, but different altitudes provide different measurements that tell us about different aspects of the upper atmosphere. Nick or Paul in particular, do you want to add to that?
I do want to add to that. And Bruce referred to how at great distances our instrument is able to make images of the planet and the atmospheric ingredients. But it's just as important on the times when we're rising up above the planet, we look sideways through the uppermost layers of the atmosphere. And when I say uppermost, I mean thousands of kilometers in altitude. So we are still detecting hydrogen and oxygen thousands of kilometers above the surface. Those being the ingredients of broken down water, this is really an essential part of solving the problem.
And, excuse me. And of course, the atmosphere gets denser and denser as you go down toward the well-mixed atmosphere. Interesting to note that we really don't have a lot of information in the deep atmosphere. Some of the current orbiters are focused primarily on remote sensing and spectroscopy and so on. And we have a couple of measurements way back from Viking, and they're kind of one-point measurements as the aeroshell went down into the atmosphere, supporting the landers. There was some really interesting data obtained, but we're really just going to get hundreds of these measurements over the course of the primary mission. So the orbit allows us to do that. It allows us to look at different local times and day-night variations, and then of course with the many orbits look at how the atmosphere is changing, both with things that are happening on the surface like dust storms, the atmosphere is breathing in and out, and as the solar input to the atmosphere is changing. So that orbit really enables this repetitive look at the atmosphere that you need to study some of these processes.
I need to clarify part of my answer. I talked about the atmosphere going up thousands of kilometers. The technical term that we use is the exosphere, because it's really thin, so thin that actually the atoms don't collide with each other. Nonetheless, our instruments have the sensitivity that we can actually measure that very rarefied gas.
I could add to the answer as well. The Particles and Field Suite is making measurements throughout the orbit. It's important to realize that we want to understand the sun as a driver. So as the solar wind changes, the velocity increases, or the density increases, how does the planet respond? And so when we see things happening in the solar wind, we're going to definitely try to make correlations with how the planet responds. So it's really important to make these high altitude measurements to make those connections. And so that's an important part of the MAVEN strategy.
Okay, we're going to stop and take a question on the phone, and then we'll come back here. Irene Klotz from Reuters.
Thanks very much, George. This question is for Bruce. I think last month you said that there'd be enough fuel aboard the spacecraft for 10 years, primarily to serve as a communications relay after the first year of science operations. And I was wondering if the orbit would be circularized to serve that communications relay function, and if so, how does that impact any additional science from a follow-on mission, or how are you going to kind of balance off the desire for additional science with the secondary role as a comm relay? Thanks.
Well, let me first clarify that we designed the spacecraft and the amount of fuel we carry to be sure we can accomplish our primary mission. So the amount of fuel was sized so that if we have problems getting into orbit, we can recover from that. We don't anticipate that, in which case the extra fuel we carry would be able to be used to extend our operations in orbit. If things go our way, we might be able to continue to operate for as long as 10 years. Of course, that remains to be seen. We'll find out as we go through the process. The first year primary mission, we've set up what we're going to do. We have enough fuel to continue making observations in the same mode if we don't need to correct our orbit after we go into orbit. We can continue observations in the same mode for about two more years. Then what we would have to do is raise our periapsis so that atmospheric drag becomes less of a factor. We wouldn't circularize our orbit, but we'd get the lowest part out of a little bit further out of the upper atmosphere to conserve fuel. And at that point, we'd be able to continue a combination of science observations and relay operations, perhaps out to the 10-year mark. I believe that relay and science can coexist, and we ought to be able to do both of those after the primary mission until through the whole lifetime of the spacecraft.
Okay, right here.
So maybe a quick follow-up then for Mike is with both MO and Global Surveyor getting on in years, what's the plan for comm relay for InSight and Mars 2020 if MAVEN's not taking on that dedicated role?
Yeah, as you correctly point out, the two main communication orbiters we have right now that are doing science are Odyssey and Mars Reconnaissance Orbiter, and they are getting long in the tooth, and we do have to plan for eventually when they're no longer operational. So this is a concern, and for this reason, every spacecraft that we send to the red planet, and even other nations who send a spacecraft to the planet, we ask them to carry a communication device so that there is the opportunity to communicate with on-the-surface assets through the orbiters. So the plan is the analysis has been done on what the expected lifetime is and what the probability of having 1 or 2 orbiters by the time we have InSight land on Mars, and then also when we send the 2020 rover. And we're okay, and we're using, basically, MAVEN will be a backup. Mars Express may still be going, and Mars Express has the capability of doing communications with the rovers. And so we're recognizing that our spacecraft are getting older, but we're having backups so that if need be, we can call on them to provide communications.
Right here.
Marie-Michelle Limoges, CBC and University of Montreal. I'd like to know if the models of the evolution of the sun are constrained well enough to allow us to study the past impact of the sun on Mars's atmosphere.
That's a very good question. The history of the sun is one of the major outstanding problems of solar system exploration in the evolutionary area. And the observations of sun-like stars are fortunately getting better and better. And so people can appreciate that sun-like stars have cycles. And there's a pretty well-established trend of the extreme ultraviolet flux with time. They can tell how old a sun-like star is by its rotation rate. And so the astrophysics community and astronomy community have been focusing, part of that community has been focusing on sun-like stars and their evolution. An outstanding question remains the nature of their activity, and whether the early activity that's implied by their higher extreme ultraviolet fluxes at an early age also implies a lot more coronal mass ejections and solar energetic particles and stronger solar wind gusts. So we hope to be doing our science in parallel with the astrophysics community, and as that further is further constrained by that research, we will combine the two banks of knowledge in a best guess of the outcome.
All right here.
Hi, Jeff Faust of Space Review. For Bruce or anyone else on the science team, you've been working on this project now for several years. It's the day before launch. How do you feel right now? Excited, nervous, something else?
All of the above. That several years is actually 10 years since we started putting together the original concept. And it really is all of the above. I don't know how to put into words what it feels like to be down to the day before launch. But I'll tell you, it was one of the most exciting things I've done to go out yesterday and watch the rollout to the pad and see the rocket and the spacecraft inside it come out of the integration facility that it had been stacked in, and to see the MAVEN logo on the side up here. I just don't have the words for it, but it's an incredible experience, and I recommend everybody should be a PI at some point.
If I could add another perspective on this, missions like this usually start on the back of a napkin, and then they go to the back of the envelope and onto a whiteboard and PowerPoint, and before you know it, it's in the computer-aided design drawings, and it's got aluminum prototypes, and then they're wiring it up, and then they're shipping it, and here it is on the launch pad. And in a lot of ways, it's gone much faster than I thought, because there's this drumbeat of the progress that's necessary to get ready for launch. So it's been a great ride. Center received 27,000 MAVEN emails. And that sounds like a small fraction of what you've had.
All right, James.
Hi.
I'm sorry, I have James Dean right next to you there. I'm sorry.
James Dean, Florida today. In terms of habitability, I was just wondering if you could discuss a little more will your findings, is it about telling you more about what the atmosphere that used to be there was like, or is it more about perhaps just like framing the period during which the most habitable conditions would have been, or is it something else?
I see this mission as, at its core, an astrobiology mission, because one of the real intellectual drivers for Mars is understanding whether there was life or could have been life. And with the climate, why do we appear to have had a climate on Mars that could have supported life at the surface early on, and we don't today? You know, something fundamentally changed, and we want to understand what those changes were. So I really do see this as a mission about the history of Martian habitability, and of course habitability by microbes. If we think more broadly, we're understanding processes by which a planetary environment can change through time. We don't know the whole range of processes yet, but as we're starting to discover more and more planets outside our solar system and see Earth-like planets and ask about whether there could be life on those, we want to understand what makes a planet habitable and what makes a planet go from being habitable to not being habitable. So I see this as a much broader mission than just exploring the Mars upper atmosphere today and learning about the history of the climate, but that's where we start because those are the questions that we get the first answer to.
Right here.
Thank you. Tony Rice, WRAL TV, and social media, Mars WX Report. Had a question about public engagement. Was curious what the plans were for data availability. Would there be an embargo? Would it go into the planetary data system as it normally does? And would there be any plans to engage the public with the meteorologic data that you're producing here, similar to the way the Curiosity rover has produced meteorologic data on a daily basis?
We will be making data available to the public, both the public at large and the non-science team science community, the rest of the science community. Our plan is to make it available as soon as possible. As you've heard described here, though, the data is not instantly easy to interpret. It comes in a form that requires some expertise, and that means that the individual instrument teams are going to need to take time to make sure they understand how the instruments are operating, what the calibration is, and that we've applied the calibration. The last thing we want to do is put out data that is hard to interpret or has to be corrected later when we better understand the calibration. By decree from NASA headquarters, there is no proprietary period, and we are obligated to put the data into the planetary data system as soon as it's available. And we have a schedule set up by which we will do that. So we're absolutely committed to making it available. My goal is to make the data as available to everybody as possible, because then we can really get a lot of people doing science with it.
Did you want to mention the other EPO activities on the mission?
Go ahead.
Okay. So, of course, we're also spending a fraction of the MAVEN budget on educational activities, things like teacher workshops. There's a great show to be projected on the Science on a Sphere displays. We expect to go national. A lot of attention to serving underrepresented communities in science.
Okay, question right here.
Hi, Don Haladia for CBC. Question for Janet. In one of your graphics, you showed these isolated magnetic bubbles. Did Mars once then have a more extensive global magnetic field? And when did it break down, maybe allowing more atmosphere to be stripped away?
Yes, the Mars Global Surveyor mission first measured those crustal magnetic fields, and the crater record and others' knowledge of the way magnetic fields and dynamos work has led the community to conclude that there was probably an early global dynamo of Mars with a stronger dipole field, and the dating suggests that it disappeared around the time of the atmosphere's disappearance at about 3.5 billion years of age or ago. So that we are examining the processes that started at about Mars being 1 billion years of age, after the initial period of internal dynamo activity and strong magnetic field presence.
Okay, we'll take one final question from Bill Harwood, and that will wrap us up.
Simple question. I'm sure it's in the press kit, but what is the data that comes back? Is it, what part of the orbit are you doing that? Is it continuous? How does it get back?
We are collecting the data on board and storing it on board. We'll send it back twice, once we're in orbit, once in our science mapping orbit. We'll send it back twice per week. You will have seen on the model of the spacecraft that the high gain antenna is body mounted, it's fixed. That means if we want to point at the Earth, we have to point the whole spacecraft. And that means we aren't making our complete set of measurements while we're sending data back to the Earth. So there's a trade-off between how often we want to do that and take away from the science measurements versus how much data we can send back. We've settled on twice a week.
All right, in that event, that's going to wrap things up. Just a couple of notes. The website is www.nasa.gov/MAVEN. Our launch coverage on NASA TV on Monday morning begins at 11 a.m. That coincides with the start of fueling of the Atlas V. And now we're going to show you, to conclude our activity this morning, our briefing, is an animation of the evolution of Mars as a wet planet and into a dry planet that explains somewhat about Mars evolution. And thank you very much for coming.